Welcome back, everybody. So here we're going to be looking at the intersection of two planes. So when two planes intersect, there are two quantities that we might be interested in. One is the angle between the two planes, and the other one is the intersection of the two planes. Now, clearly, if two planes intersect, they will intersect along a straight line. So the intersection of two planes, if they intersect, would be a straight line. So here, capital L is the line of intersection of the two planes, and theta is the angle between the two planes. So here, P1 and P2 are two planes, and theta is the angle between them. So now n1 is a vector perpendicular to the plane P1, n2 is a vector that's perpendicular to the plane P2. Now, I claim that the angle between the two planes, theta, is the same as the angle between the vectors n1 and n2. Here is why that's true. Now, so here is a portion of the plane, right? So here, if you look at the green vector right here, a1, and the orange vector a2, so this orange vector a2 is on the orange plane, and the green vector a1 is in the green plane. So the intersection between the two is theta. Now notice that if I rotate a1 by 90 degrees, then I'm going to get n1, and if I rotate a2 by 90 degrees, I'm going to get n2. Well, I'm not going to get n2 exactly, but I'm going to get something parallel to n2. So if I rotate a1 by 90 degrees, I get a vector parallel to n1. If I rotate a2 by 90 degrees, I get a vector parallel to n2. So basically then, if you imagine that you are rotating both of these vectors at the same time by 90 degrees, then you're going to get vectors parallel to n1 and n2. So it's clear that the angle between the planes would be the same as the angle between the two normal vectors. So to find the angle between two planes, you just find the angle between their normal vectors, which we already know how to do. So let's say that the equation of the plane P1 is 2x minus y plus z is equal to 0, and the equation of the plane P2 is x plus 2y minus z is equal to 1. Now, what would be a vector perpendicular to the plane P1? Well, in order to find a normal vector for P1, we just read the coefficients of x, y, and z. So 2, -1, and 1. That's a vector that is normal to the plane P1. And for P2, if we look at the coefficients of x, y, z, we get 1, 2, and -1. So this is a normal vector for the plane P2. So then we find the angle between n1 and n2. So if theta is the angle between n1 and n2, then cosine of theta we know would be given by the dot product of n1 and n2 divided by the length of n1 times length of n2. So n1 dot n2 and n1 dot n2 is 2 minus 2 minus 1, which would be minus 1. Length of n1 would be 4 plus 1 plus 1, which is root of 6. And the length of n2 would be 1 plus 4 plus 1, which would be 6 as well. So I get root of 6 times root of 6 here, and we get -1 over 6. So theta would be cosine inverse of -1 over 6. So whatever angle that is, that's the angle between the two given planes here. Let's say now that we want to find the intersection of the two planes. That is, we want to find the equation of the line L, which is the intersection of the planes. How do we do that? Well, in order to write down the parametric equations of a straight line, we know that we need a point on the line, and we need a vector that is parallel to the line L. So the first question is, how do we find again, to find the intersection line L, to find the parametric equation of L, we need a point on L, and we need a vector parallel to L. So how do we find a point on the intersection of the two planes? Well, to find, because the intersection is a straight line, so that's an infinite line. So, at least two of the variables take on any real value. So what we're going to do is we're going to set z to whichever value we like. So we're setting z to 0, and then we're setting z to be 0 in the equations of the two planes. And so here and here we're going to set z to 0, and then we're going to get two equations with x and y only, and then we can solve for x and y. So we can solve these two equations simultaneously. So from this equation I can solve for y, that's going to give me 2x. Now I plug that in here, so I get x plus 2 times 2x, which would be 5x here is equal to 1, so x would be 1/5. And then if x is 1/5 here, then I see that y would be 2/5. So because I got the point P to be 1/5, 2/5, and 0. So the point is, by picking z equals to 0, we now have two equations and two unknowns, and we can solve for the two unknowns here easily. So then we get this point 1/5, 2/5, and 0. So this would be a point on the intersection of the line, on the intersection of the two planes. Now, if z equal to 0 doesn't give us a intersection here, that is, if it turns out that when z is 0, these two equations cannot be solved simultaneously, then what we do is we set another variable to 0 instead of z, and then we do the same thing. Now, to find a vector parallel to L, so how do we find a vector that's parallel to L? Well, to do that, imagine that I bring these two vectors at this point. So the line L belongs to both planes. So N1 and N2, both of them are perpendicular to L. So if I take the cross product of N1 and N2, that's going to be parallel to L. Again, N1 and N2, both of them are perpendicular to L. Therefore, the cross product of N1 and N2 would be parallel to L. So we take the cross product of N1. So we already have seen for the given planes, N1 and N2 are these two vectors. So we take their cross product now. So the cross product would be given by the determinant of ijk. First row is N1, second row is N2, and then we compute this cross product. What we're going to get is negative I plus 3j plus 5k, which is negative 1, 3, and 5. So this would be a normal vector this would be a vector parallel to the line of intersection. Recall that this is a point on the line, so now we can write down the equation of the line. We know that the equation of the line would be given by x is equal to p plus t times n. So I remember x is xyz, so that's equal to p. P is 1/5, 2/5, and 0, plus t times n is minus 1, 3, and 5. So we see that x would be 1/5 minus t, y would be 2/5 plus 3t, z would be 0 plus 5t, and so that's the, so we got the parametric equations of the line of intersection. Here are the symmetric equations of the same line. So here, if I solve for t, I get minus x plus minus. So if I solve for t, I get 1/5 minus x. Here, if I solve for t, then I get y minus 2/5 over 3, and here I get t to be z over 5, and they will be all equal. So this would be the symmetric equations of the line of intersection. So just to recap, if you want to find the angle between two planes, then just find the angle between their normal vectors. That's number one. Number two, if you want to find the equation of the line of intersection of the two planes, then we need a point on the intersection, and we need a vector that is parallel to the intersection. Well, since n1, since the normal vectors n1 and n2 are both perpendicular to L, their cross product would be parallel to L. So that way we can find a vector that's parallel to L. And how do I find one point on the line of intersection? Well, to find one point on the line of intersection, we know that it's an infinite line, so at least two of the variables, if you think about it, when you have a straight line in 3 space, at least two of the variables will take on values from, well, if you have a straight line in 3 space, at least two of the coordinates of the line will take on any value between negative infinity and infinity. So the idea is that, okay, set one of them to 0, so let's say z, you set that to 0, and then you solve for x and y simultaneously from the equations of the two planes. Now, if that doesn't work, then you set one of the other variables to 0 and then do the same thing again. Okay, so this is it on this example, and we have more examples coming.